when Roger has finished taxing. We have Johan speaking about Morse growth reads and blah blah blah.
Thanks. So I will first talk about the correspondence between holomorphic strips in T star M with gradient flow lines. And then the second part I will talk about Morse flow trees. So throughout the talk I will assume that I will just fix some n-dimensional smooth Riemann manifold. Okay. So I'll consider the cotangent bundle of M with omega minus d e to q. And then I will pick a Morse function on M. Smooth Morse function. Smooth Morse function. Maybe I should split this. And then I will consider the two Lagrangians in the cotangent bundle, the zero section, and the graph of the f. So the graph of the f, this is points or tuples q, and then the differential of f in q, where q is a point in the base. And since f is Morse, the graph intersects the zero section transversely, and also the intersection is the critical point set of f. So the idea is to consider holomorphic strips that maps into the cotangent bundle with boundary on the graph and on the zero section. And then somehow squash this holomorphic strip, and the idea is to get a gradient flow line in the base. So I'll try to talk about how this works. So pick. So I want to talk about holomorphic disks. So I'm gonna pick some almost complex structure, or a one parameter family of almost complex structures. Of smooth almost complex structures, and then 4 intersection points between the graph and the zero section. I consider the moduli space of maps from the unit disk in C into the cotangent bundle, such that the boundary maps onto. Sorry, not the disk. I'm considering the trivial strip. So the first part of the boundary maps into the zero section, and the other part of the boundary maps into the graph of the gradient. And so d bar j. So d bar j is 0. Map U. Whoops. and at infinity they map to the intersection point. So then there's some statement. If f is c too small enough, there exists some omega compatible family of almost complex structures such that the projection from the space of homomorphic strips into the smooth maps from R to M, which takes a holomorphic disk and takes the second map sets T to 0. This is a bijection onto the set of bounded trajectories of, I just write minus df. So the bounded trajectories of the negative gradient flow of f. And yeah, connecting x. I want to say something about the proof in one direction, which is if we have a flow line, then we get a holomorphic strip. Essentially, we take the gradient flow line and sort of lift it with the flow of a certain time module. So first I will just write down this Hamiltonian, which takes the value of f in the first component, and then we consider its flow, which just takes the first component to the first component, and then t the f at q. So this takes the time one flow of this flow takes the zero section to the graph. Then we sort of find this almost complex structure, so we can show that it gives us a disk somehow. So we can first take a almost complex structure on the base, define J0. We can lift it by conjugating with the differential of the flow. Gives us a family of one parameter families on the one parameter family of almost complex structures on P star M. Then if we pick some path on M, we just sort of lift it.
Sorry, what is J0?
J0 is the almost complex structure defined here on M.
I don't understand this G.
Oh, so G is the metric on M. So if I evaluate this at W,
Okay.
is it fine? So I define x bar as the time t flow of x tau, 0. So I take this, insert it into the first component, and just flow upwards. So the statement is if, or claim, if x dot. So if x is a negative gradient flow line, then the bar j of x bar is 0. And this is just a computation of, you write out the actual derivative. And the other direction is slightly complicated, but so this direction doesn't use that f is c too small, but the other direction you need that.
Sorry, I'm still trying to understand. So you fix the metric on n
Yeah.
to start with?
Yes.
So yeah, on the zero section you have the cotangent direction and the tangent direction, and those are dualized. I mean, they're isomorphic by g, and j naught just sends one of those to the other.
But then it's defined only at the zero section.
It's defined only on the zero section. Is that correct? That was my understanding.
G is on M.
But J0 is those, if you...
J0 is, yeah, it's defined on the zero section inside
Yes.
of the cotangent bundle.
Yes.
Yeah.
Yes.
And JT is defined on the flow of that by the...
Yes.
By the Hamiltonian.
Yes.
So how is it defined on the zero section?
It sends every tangent vector to the cotangent vector that's paired with it by g. So a tangent vector is a tangent vector to the zero section. Yeah.
Yes, this gives sort of a correspondence between homomorphic strips that has its boundary on a graph with negative gradient flow lines. In a similar, or like you can generalize this to the situation where the boundary lies on several graphs, and then you would get something like a tree, with each sort of edge in the tree being a parameterized flow line of the corresponding component of the graph. It's negative gradient flow. So this work by Fukaya and O. And this is sort of the motivation. We would like to bring this into the Lechangerian world. Now we consider the one-jet space, which is sort of the compactization of the cotangent bundle. So we pick alpha to be dz minus, what did I pick in pdq, and then we consider the Lechangerian submanifold in here. Okay, so to compute the Lechangerian compact homology of this Lechangerian, we want to compute or count holomorphic disks mapping into T star M and has its boundary on the Lagrangian projection of L. This is all fine, but a priori we cannot relate the disks mapping into the cotangent bundle with boundary on this Lagrangian because this is not a graph. So we can't directly sort of apply the correspondence of Fukaya-O. Not graphical. So I will use some notation. the base projection I will denote by pi, and then the Lagrangian projection by pi L, and then the front projection by pi F. So then we will first assume that L has simple front singularities. So this has a precise meaning, but I'm not going to write it down. But essentially it means that L, or the front projection of L, only has sort of cusp singularities, except in dimension 2 and dimension n equals to 2, so dimension 5. Then L is also allowed to have swallowtail singularities, and everything still works if you allow swallowtail singularities, but I won't say anything about it.
Why would you only restrict that to n equals 2 instead of that times products in higher dimensions?
Good. Can you repeat?
Can't you allow swallowtails to appear in higher dimensions also? Or is it specific to n equals 2?
Swallowtails are okay, but that's about it.
Okay.
That's just because of the codimension. You can make them not touch the swallowtail point.
Yeah, I'm not sure. I mean, I guess it's okay in high dimensions.
The swallowtail is, that swallowtail exists on dimension 2, in high dimension or something.
Oh, yeah, okay, yeah, so it's the...
Isn't
Right, but I think it
swallowtail
doesn't
codimension
involve it,
2?
But maybe it can be done.
I think that would be
Yeah.
more complicated. So sorry, how restricted is this assumption?
In dimension, or in n equals 1, it's not
Yeah.
restricted because then it's everything's generic, so you can perturb. But in high dimensions, I'm not sure how restricted.
It's not in dimension 2. With n equals 2, if you're allowing swallowtails.
Say that again. Yeah.
In dimension 2, all you need is swallowtails.
Yes, yeah. But
But in higher dimensions, yeah, it's restricted.
okay. Yeah, I mean, in higher dimensions, you assume that it's only has cusp.
So then it's even more restricted.
Yeah, sure, of course, yes. But I mean, if you wanted a measure for how restricted it is.
I mean, we don't even know in general what are the singularities in the arbitrary high dimensions. There is a
Yeah.
specification by Arnold, I don't know, some classification up to certain dimension, but
Well, it's a larger value.
yeah.
Okay, so I mean, we'll mostly I will only think about singularities as being cusps.
So we're not allowing swallowtails?
We are, I mean, yes, but I won't say anything about it. Everything, I mean, all arguments still work if you allow swallowtails, but I won't say anything about it. Yeah. So despite the Lagrangian projection not being a graph, we can still do something. So I will denote the cusp edge by sigma, singular set. Then you pick some point in M outside of the projection of the singular set. Then we can consider look at how M lifts to the knot. So consider the pre-image and then the pointed down L. And we'll assume that this has or contains R points. And if we pick a neighborhood around this point then this neighborhood also lifts to a disjunct union of our neighborhoods. So around each point we pick a neighborhood and look at the disjunct union of these ones in dot. So then the key point here is that the front projection of any of these neighborhoods lie in M cross R, which is the sort of zero jet space. So this UI is a graph of a function which I will call fi and is defined in U. And also similarly, the Lagrangian projection of UI inside of the cotangent bundle is a graph of dfi, so the corresponding fi. So instead of instead of being a graph, it's the front is the graph of a multivalued function. I'm going to try to draw some picture. So this is U, and then this is U1, and then it's U2. So each of these, if you consider a seat in the front, so I drew the front. This is a graph of a function, or each piece individually. So these functions we can also consider like their locally defined gradient. Minus the gradient of fi minus fj, which is defined where in Okay, so the last thing we need is lifting of paths. So consider a path. So then we consider we define its one jet lift as an unordered tuple of two continuous lifts . Such that either they are not the same, so somehow they lie in different sheets. If you think about the sheets when you take the front projection, or they coincide, and they meet at the cusp. I guess this is. So then also we can consider the cotangent lift, which is you take each of these components and just take the Lagrange projection.
So these are lifts to L?
Yes. So if this path then satisfies the gradient flow equation, then we say that gamma is a flow. Is a let's see. Is a flow line. Flow line of L. And oh yeah, so F1 and F2 here is the I'll just say it in words. So the F1 and F2 are the the functions whose graph is the sheet in which the lifts lie in. So you take the one jet lift and get a couple of paths. Then gamma tilde 1 lives in one sheet, which is defined by F1. And correspond.
Sorry. I don't know. Can you maybe draw them on this sheet or something? I don't know.
I mean,
it's easy.
So
You can use some color.
this is the path in M, so it lifts to sort of a pair of paths here.
That's the first case.
Yeah.
And then the second case is.
So in the second case, you need more dimensions. So they what am I trying to say here? I mean, I guess what I'm trying to say is that either maybe I mean maybe I mean this.
No.
I don't. No, there you go. There you go. I mean, what I imagine is that they meet in sort of the cusp here, but they're not the same. Maybe I mean, I don't know.
Zero.
Yeah.
Say
What
again?
is T0?
The is
Yeah.
point. I don't know. I'm confused now.
So the first for all P and the second for sum is just for T3?
So the,
So the second one is the agreed at point T0 such that it leads to a cusp.
And what happens after
In particular,
T0?
you want T0 probably to equal 0 also.
Or 1?
is T0 0 or not?
Because otherwise, if you just
No.
have a path that like goes past the cusp or something.
T0 is some point
Some
in the
point in
center.
the
Yeah.
It's just continuous.
When you
like-
pass
I'm
through the
thinking
cusp.
You want it to be just the beginning, yeah.
Or are you staying in the? You don't stay all for all time. You just pass through.
Yeah, I think you want to pass transversely.
Okay, and you just have one lift in this case. That's what is written.
It's
Ah, you
connected.
just sort of You just kind of switch sheets as you.
If you're modeling the switch, then it's
The path
off.
the path is like tangent to the singular edge, and as you go like a lift along that path is going to like hit the cusp edge and then go to the next sheet. That's what you're saying. So like the projection is
Right.
actually tangent to
Right.
to like the singular edge. So if you draw like the cusp, it's going up. So if that's sort of the picture.
Yeah, but then there's no sense in which gamma 1 tilde is equal to gamma 2 tilde.
Yeah.
Well, it
Is
just means like
one of them is on a completely different sheet, right?
no. You just your pair is just a repeated thing.
Yeah.
You don't lift twice. You just lift once,
Yeah.
but you still want to refer to the pair. I think
It's connected instead of disconnected.
Oh,
you have a connected lift, so there's just like one path, but you write it twice.
hang on, so
Somehow
before you, except at the cusp edge, you're still flowing on the difference of two functions, right? So what are the two functions? So one of them I see there, the other one isn't it hidden somewhere else?
Sorry.
This is not a path that's dying at the cusp, right? It's going through the cusp edge.
Yeah.
So it's locally given by the gradient flow for the difference of two functions. One of the functions is there, but then the other one is somewhere else.
I mean,
There has to be
this
a
is
third
F1,
sheet
this is
somewhere.
F2, sorry. There are different sheets, but they meet in the middle.
No, yes, but there's a third sheet, and then you flow on the difference between, say, F1 and F3 for a bit, and then or I guess the other way around, F2 and F3, and then switch to the difference between F1 and F3.
Yeah, I see what you mean.
What if there is no third sheet?
Then this doesn't exist.
Yeah.
Ah.
Then it's like in the
If you have,
It just, it doesn't extend
if you have
the
the
grading
tree,
flow
you
line,
have
it
to
just
have
skips
three
at
stuff.
that point.
and then you have to
That's
have
a different picture. That's the
Zero,
picture
one,
they-
one.
they just sent in.
But now I'm very confused.
Yeah.
You're on the switch.
Yeah.
What happens in
Oh, I
the
don't
end?
know. But that
I
picture
agree,
is-
I agree that picture is the switch. I thought you were describing it. Because we were discussing the T0.
And you stop it again.
So we were discussing
And
the
then
campaign
there's a
inequality.
weird thing.
Yeah, is this the one that?
Is this a cusp band or a switch?
Oh, yeah.
Yeah, if it's a cusp band, then it's something else.
Yeah.
I mean,
So
I think it's-
I misguided you. I think you were trying to explain the cost
I think we're trying to define the full lift, and maybe you will not describe a cusp edge, but the switch has not appeared yet. And so please, that picture, if we all agree, maybe shouldn't be there.
Yeah.
I was just.
So the second thing is gamma 1 tilde. So either they never coincide or they're only allowed to coincide at a cusp point.
That's what I think I thought before.
Yes.
Before I got a bit confused.
The beginning and
What?
You were written there.
But then it also doesn't progress past that point, right?
Yeah.
So it's not a path from 0, 1 unless T naught is equal to 1. That's okay. Yeah.
Yeah, sorry.
I'm just saying it's not what's written there.
What's written if I write if gamma 1 is equal to gamma 2, then gamma t is to
Yeah, maybe.
Yeah.
Oh, yeah, I think maybe it means that. If gamma
That would sort of
1
make sense when
Yes.
they meet at the cusp, yeah.
Yes.
So either they never meet, or if they do meet, they
Yeah,
don't
I mean
meet till
that's
the
what I
end.
thought, but then I got yeah.
Yeah, okay, so
But
if
if-
gamma
if-
1 of t is
then-
equal to gamma 2 of t,
then gamma
T1.
or at
F1.
1,
Oh, okay.
2. Yeah.
then t is equal to 1, and
Yes.
And then gamma
Yes, right.
T1 left at the cusp.
Yes, yes, yes.
okay, that's if. If.
Yes.
Okay, then,
Then
I don't know, I'm not sure that's the correct stating.
And then
And t is equal to 1, or what?
And G is
it has to end.
oh T equals
Well, which end?
I mean,
Start end or the end end?
Well,
And end. Well, either,
I
right?
mean,
Okay.
and t is equal
And
to
t
0
or
or
1.
1. Yeah.
But then there's a direction.
Huh? Doesn't it follow?
It's the negative gradient.
Yeah, maybe.
yeah, so T gamma.
It has to be t equals
T
Yeah.
equals 1.
And t equals 1.
Okay, well, we can try that.
Let's pretend we understand.
Um, so I guess this was said during the discussion that, at least I thought I heard it, the one jet lift we may orient it by just looking at the gradient flow and taking the lifted orientation. Orient. According to the lift of negative gradient in the point. So- Um, maybe. We orient the first one according to the negative gradient lift of this thing, and then we orient the other one opposite. Okay. this we may define what a flow tree is. So a flow tree of L is a continuous map phi from a source tree into M, and we'll assume that this source tree has finitely many edges. And that if V is maybe I just try it. So if V is a vertex, then all adjacent edges are cyclically ordered. Sorry, adjacent. So A, if we restrict to an edge, it's an injectively parameterized flow line.
Shouldn't you assume from the beginning that gamma is a tree? Here.
Say it again?
Should you assume that gamma is a tree?
Oh, yeah.
This is the most basic one.
Tree such that.
Yeah, okay.
Yes, sorry. B. So if V is a k-valent vertex and the adjacent edges are E1 to EK, then we consider the cotangent lift. So I will drop all reference to the map phi and just sort of think of the edges as already living in them. It's cotangent lift. Then we require something. We require that for all I, where k plus 1 equals 1, quotation marks. So we require that they sort of glue together in the Lagrangian projection. And see, so this condition gives that they glue together to a curve in the Lagrangian projection, and see, we say that this curve in B is closed. So if we drop the condition C, we get something like a partial tree. But I won't really say anything about them.
Do you put any data on the lengths of the edges at all?
Not right now. I mean, I'm not today.
Oh.
Maybe do at some point. I don't know.
Can you draw some picture?
Yes. Maybe I can. Yeah, in that. I want to define a puncture first before. So I'm right now I'm not drawing any pictures, but I will in a second. So if we have a flow tree, consider a k-valent edge vertex. I mean, so yeah, with adjacent edges E1 to EK like in B, such that they're paired up. Like the cotangent lift of EJ2 is equal to the cotangent lift like this. So we pick a flow tree and then a vertex and take the edges so that they glue together like in B. Then we consider the one jet lift of the corresponding edges. Instead of a bar, we have a tilde. So if they are not equal at the vertex, then so then I will say D is a puncture. So technically, I think in Tobias' paper he writes that D contains a puncture because a priori we can have like several pairs of these kind of things that don't agree in the vertex. So a priori we can have sort of several punctures associated to one vertex. But if that happens, you can always split up the tree into smaller parts where each part has only vertices with at most one puncture. So we can just say that we assume, I mean, without loss of generality, we assume that they vertices can only have a puncture and have one puncture, and in this case it is a puncture. So the sort of picture. So the terminology is to conveniently line it up with the disk case. So if I draw the part of the unknown. And then so this, we should imagine that this is the one in the one jet lift. Then at this rave chord, they. Oh yeah, so it's okay. I maybe should have written it. If these two guys are not equal, then they equal rave chord ends. So they equal rave chord ends, and they have opposite orientation. So they, I mean, in the Lagrange inflection, it looks like this. And this is sort of the E to Ej equals to E to 1 J plus 1 E. So this is E to J, and this is E 1 J plus 1. You can say that these punctures are positive and negative as well, which should line up with this case. So if towards E to J D and sort of the Z component is less than then if the other inequality holds as negative puncture, and also if you orient it otherwise it's negative, and if you split this as well. So also like in the case with disks, every tree has at least one positive puncture. And the proof is more or less the same. If you consider the negative integral over the one jet lift of the tree and integrate PDQ, sorry. No. And then just use that as Legendre and then use Stokes' theorem. It's the sum over positive punctures and the difference in z-coordinates of the Reb chord. Sort of the length of the Reb chord minus the sum over negative punctures and the length of the negative. So you show that this is greater than 0. And instead of saying that this is the area of the disk, so to speak, this can be, if you split this up and integrate over all individual edges and write it out with you use parametrization and then you write it as the gradient of f and then you see it's positive. So then, and I don't have time to do much more. But you can define sort of the dimension. Maybe I need this as well. So you can define the dimension of a flow tree by sort of computing a Morse index of the punctures and some Maslow content of the non-punctures, and then you sum them up in an appropriate way and you get some dimension. So the point is that the dimension 0 flow trees, they form a manifold. So these rigid flow trees, they're finitely many in certain in the correct setting, and it's well defined to sort of count them. And of course, we want this count to be line up with the count of disks. So the dimension, also the point is that the flow trees are easier to work with than with disks because they're easier to count somehow. So the dimension 0 trees, they only come in certain, like the vertices can only look a certain way. I'm gonna try to draw the list of all the vertices that can appear and the corresponding part of the tree. So that if a vertex is a one-valent puncture, then the corresponding disk part is this. In the front projection you have something like this. And the tree is, if it's a positive puncture, it's oriented outwards. So 2 valent punctures.
Sorry, what is the shaded part?
Sorry, a second.
What is the shaded part?
Oh, so the shaded part is supposed to be the sort of corresponding part of the holomorphic disk. So if you were to count sort of this puncture, when you count the count of a disk, it would be the corresponding tree part. So in the Lagrangian projection, if you count something like this, maybe we'll use a little. And then we have y0. So this is kind of hard to draw now. Try. there's sort of the disk splitting into two, and the corresponding tree is a three-event vertex. Next we have the end. And we have a switch. And not going to draw anything here. So this path goes from the sheet that's below, and then it goes tiny into the cusp edge and sort of switches sheet. And then we're supposed to have something like sort of a curve down here. So this is a two-valent vertex, which sometimes you draw a dotted line to record that it's a cusp there. And then we have the last one. There's a three-valent thing with the cusp being. So these are all the vertices that there exist. So, and also the. So I'm running out of time, but also sort of the main theorem, which I didn't have time to state, but it's that dimension zero flow trees. They correspond to rigid zero-dimensional holomorphic disks in the cotinate boundary on the Lagrangian projection.
You know, better state.
Yeah, maybe you should
just
try
write
it.
it down. Then it's mostly.
So there's also a lot of, yes, I mean, essentially very, very, very simplified. The proof is more or less the same as in the Fleur case. You just squash the disk down and then you have to do something. So what I mean with squash down is you take the fiber scaling and scale it in the y and z directions, and then you make it you make lambda very small, and then you have to do some more perturbations around the cusp edge, and yeah. So the state now written down is so. Let's. I'm not sure how to. So J-homomorphic disks with boundary on. Okay, maybe I can give this a name. So this fiber scaling is S lambda, and then L lambda is just the image of L, and this tilde is more than one perturbation, I think, in the end. With at most one positive puncture are in one-to-one correspondence with rigid, meaning dimension 0 and more, transversality stuff, flow trees with one positive puncture, determined by L. So we'll hopefully see some examples maybe tomorrow when we talk about not contact homology. Yeah.
Are there any questions?
Maybe for it, you do the trefoil that was done this morning in 30 seconds.
Say again?
Just draw the tree, one of the trees for the trefoil that Marco drew this morning.
Yeah.
So
Not a good prediction.
That's okay.
Alright, okay.
No, it's fine. It's fine.
I mean, okay. So the disk here, if I draw plus, minus, 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 so this B1, B2, B3, A2. So this, I mean, this tree would be sort of start with a positive puncture, and then you have to stretch it out to see. You have positive puncture going out, and then you pass a two-valent puncture here. So you will get, I'm not sure about orientations here, but we'll get two more two-valent punctures, and then we have an end here. So end, two-valent punctures, and then one valent positive. So that would be for sure. I mean, it's in dimension 1. It's almost stupid.
Because you only have linear trees, or?
No, you can have these,
Ah,
but that's about it.
okay.
So once again, so if I understand correctly, that the limitation of this technique is just infinite generality is on dimension 5, because we don't have control over singularities from a general type in high dimensions. Is it
I
correct?
think so. I'm not sure about really detailed details, but yeah.
Okay, let's thank the speaker again.
So we're done with the talk, but I guess if there's open discussion or if Lenny has something to do, something to say, or if Roman has something to say to sum up the day, then I think step forward.
Good job, everyone.
Yeah, it was a nice day. So if you have some questions, I mean, at least I am around.
Yeah.
It works the same way for